The second concurrency we'll study for a triangle is the concurrency of the triangle's three angle bisectors. So first of all, we're going to need the definition of what an angle bisector is, but then also we'll need an alternative characterization, a consequence, a theorem that can be arrived at from this definition that will be necessary when it comes time to prove the concurrency of the three angle bisectors of a triangle. So what does it mean to be an angle bisector of, in particular, the vertex A in the triangle ABC? Well, that will be a line, we'll call it L, that passes through the point A and which divides the angle at A into two equal parts. To be precise about that, we can say that if I pick a point P on the line L but on the same side of A as are B and C, then the angle CAP, so the angle on the north side of the red line, if you like, and the angle on the south side, BAP, of the red line, will have the same measure. So the angle just is divided in half by the angle bisector. That's the original definition of what an angle bisector is. Now, note here, this is something that I've definitely screwed up in the past, that the angle bisector of an angle does not necessarily bisect the opposite side. So we don't know, for instance, that it's the case that these two lengths on the opposite side are equal to one another. So just be careful about that in general. An alternative characterization of the angle bisector is as follows. If L is the angle bisector of the angle at A, then all of the points on that line L are equidistant not from the vertices, as we had with the perpendicular bisector, but rather they're equidistant from the adjacent sides at the angle A. So if Q is any point on this angle bisector L, then if I measure the distance from Q to the side AB, and when I measure that distance, I take it at a minimum. I take it at such a way that I drop a perpendicular from Q to AB, and I measure the length of that segment. Then that distance, and the distance from Q to the other adjacent side, AC, are equal. So that's an alternative characterization of what it means for a line to be the angle bisector at A. It consists of all those points which are the same distance away from AB as they are away from AC. And again, don't forget, an angle bisector does not actually necessarily bisect the opposite side of the triangle. So just because it cuts the angle in half, it still probably does not cut the opposite side in half. You'll have to take a moment and convince yourself why that might be the case. Okay, so what can we do with angle bisectors in a triangle as a result of these definitions? Well, suppose that we take all three of the angle bisectors of the triangle ABC. Then the angle bisector at A, which cuts the angle at A in half, and the angle bisector at B, which cuts the angle at B in half, and the angle bisector at C, which cuts the angle at C in half, those three angle bisectors are all concurrent. They all meet at a common point. We're going to call that point I this time. And if we take a look at the alternative characterization of angle bisectors, we'll see that that means that the point I, because it lies on the purple bisector, it's equidistant from AB and from AC. Because it lies on the green bisector, it's equidistant from AB and BC. Because it lies on the orange bisector, it's equidistant from AC and BC. And therefore, it's equidistant from all three sides of this triangle. If I'm standing at that concurrency point, I can reach out and touch each of the sides of the triangle with a segment of the same length. That therefore implies that we can sketch a circle with that concurrency point at its center, which will exactly touch each of the sides of this triangle. And as a result, we call that concurrency point the incenter of this triangle. And the circle, which we draw using the radius equal to the distance from the incenter out to any one of the three sides, that circle is called the incircle of this triangle. And as a result, it has been inscribed inside of this triangle ABC. So just like with perpendicular bisectors, where we were able to circumscribe a circle, called the circumcircle, in this triangle that passes through all three of its vertices, and has the circumcenter, the concurrency point of the perpendicular bisectors, at its center. If we exchange lengths with angles, exchange sides with angles, and look at the angle bisectors, we get a similar notion, except instead of passing through all three of the vertices, the incircle of this triangle touches all three of its sides and has as its center the concurrency point of the three angle bisectors that we call the incenter of the triangle.